Okay, so let's take a look at today's lesson. Today's lesson is the first of our volume lessons. This particular type of volume is called known cross-sections. And that's because, as you can see, I've got some of these figures up here. For this particular figure, the cross-sections are squares. For this particular figure, they are semicircles. And so one of the issues that students have with volume in general is really understanding and visualizing what in the world they're doing. We're looking at things in 2 dimensions, and we're finding volume for things in 3 dimensions. So what I wanted to do, I have some, I want to go through and talk to you about the visualization of it, just so we can get a bit of a better idea on what exactly is it that we are calculating. So in this instance right here, we have our base is a circle, and we're going to use squares. We're going to see squares. And as you look at the square, you can tell that it is perpendicular to the x-axis. That is very significant. When the cross-section is perpendicular to the x-axis, we have to have our equation in terms of x. So as you can see, this changes size as it moves across our base. So if we accumulate all of those squares, it creates a 3-dimensional figure that would look like this. And that's the thing we're going to be finding the volume of. Okay, so that's what would be created if our base was a circle and our cross sections were squares. It would create a solid such as that. So let's look at the same base using equilateral triangles. All right, so we have the same base, it's just still a circle. We're going to look at the equilateral triangles again, perpendicular to the x-axis. As they move, you can see they change size and area, but we refer to that as a cross-section. The cross-section is a equilateral triangle. As we accumulate them and they continue, the ones behind stay, it create a 3-dimensional figure or a solid that would look like that. And that would be what our solid would look like that we're going to be finding the volume of. Let's look at what if our cross-sections were isosceles right triangles. And isosceles right triangles, they could have you put the side as the base that's touching our circular base, or the hypotenuse. I've seen several. This one of the sides is touching the base, and so that would be our cross-section. Notice again, it's perpendicular to the x-axis, so that means our equations will be with respect to x. If we accumulate all of those triangles, this would be the figure that we're going to be calculating the volume of. Okay? And the last one, let's change the base. Let's look at a base that's a right triangle. And we're going to our cross-section is going to be a semicircle. And this time, look at this time, we are perpendicular to the y-axis, which means that we're going to be using y's in our equations. So this would be perpendicular to the y-axis. If we create the solid, leave all of those cross-sections whole, it's going to create a figure that looks similar to that, and our solid would look something like that. So that gives you a bit of a visual on what it is we're going to be calculating the volume of. Now, for some of us, this is going to be delightful news. You do not have to be able to visualize every single cross-section figure, 3-dimensional figure that you're going to be finding the volume of, because I know for some of us that is a challenge, visualizing things in 3 dimensions when we only have them in 2 dimensions. So let's take a look and see how we find the volume of these objects. If we are looking at the cross-section of area taken perpendicular to the x-axis, then our formula for volume is going to be the integral from a to b, and that's the region that's bound by the base of our solid. Area with respect to x dx. So we need to come up with an equation for area, and we integrate it. And that kind of makes sense. areas in 2 dimensions, and when we integrate something in 2 dimensions, it would make sense that that would put it in 3 dimensions. And that's how we were finding volume, is we're integrating the area of one of the cross sections. If we are perpendicular to the y-axis, then our volume formula, we still bind it by A to B, but now our area is going to be with respect to y. We're going to have y's in our equation, and we're going to integrate with respect to y. And those are our formulas. All we have to do is find out what the formula for the area of whatever cross-section we're going to be using, figure out how to represent it with algebra, and integrate. And we will be using our calculator on this lesson entirely. So that's the formulas that we're going to be using. So let's look at our first example. It asks us to set up the integrals needed to find the volume of the solid whose base is the area bounded by, and they give us some curves, y equals x squared and y equals negative 2x plus 3. So just like when we were doing area yesterday, I would like for you to draw the base for me. Draw me a picture. Okay, if you use your calculator, just sketch what you have on your calculator. We have y equals x squared, so we have the parent parabola. Okay. We have the line y equals negative 2x plus 3. So we have a y-intercept of 3 and a slope of negative 2. And our base, and I'll just kind of give it some shading, our base is represented by this closed figure right here. That's our base. We're going to use that base, and we're going to calculate 2 different kinds of cross sections. We're going to use rectangles of height 4. We're going to do that first, and then we're going to do semicircles. Okay, so the first thing that we need to do is figure, what is the area of a rectangle? We need to have the formula in our head. So we know from, years and years, and since it's referring to it in terms of height, I'm going to call it base times height instead of length times width. So the area is base times height or length times width, however you want to call it. We are already told that our height is 4, so this is going to be pretty easy. It's just going to be a 4. What's going to be the challenge for us is figuring out how to represent the base. And this has to be algebraically. How do we represent the base algebraically? Because, as you saw in those diagrams, the base exists at all of those locations. I can't just figure one location. Let's go ahead. Let's see. We are perpendicular to the x-axis. So let me go ahead and draw an example. So this would be a location of the bases of one of those rectangles. You can envision there are really an infinite number of rectangles that are there. The integration allows us to do an infinite number between the bounds. So our task is going to be to figure out how to represent this distance in algebra. How do we algebraically represent the distance? And this is so important because it's going to basically lead us into the different other volumes that we're going to be doing. We have other techniques of calculating volume. So I'm going to be real specific. Let's talk about how we find distance. All right, we're with respect to x. And we know that this line right here measures itself from the x-axis. In other words, if I were to put in -1 in this equation of the line, it would return this entire height right here. You with me? The line itself measures itself from the x-axis. So this is the distance represented by the line. All right. We don't want this entire distance, right? We don't want the whole thing. So let's talk about the parabola. The parabola measures itself from the x-axis to itself. So in other words, if I put a 2 into the parabola and I get a y value out, that's going to give me this length here, right? It's going to give me the length. So if I want this portion, I would take the measurement for the line and I would subtract out the measurement of the parabola. You with me? That would get rid of this piece that we don't want to calculate, and it would give me only the yellow. So I take the equation of the line and I subtract out the equation of the parabola. And that gives me that space that I'm at that I want. So my base I would represent by, so let's just draw our formula out. My base is going to be the line, which is negative 2x plus 3. Then I want to subtract out the parabola because all this empty space I want gone. So I would subtract out the parabola, and that represents my base. My height, we talked about before, is 4. So that represents the area of a cross-section of my, let's see, we're doing rectangles. Now to use my formula up here, my integral formula, I'm going to integrate. Let's see how we want to bind the number of rectangles by the bounds of our base. So I want to start at the x value over here, at this smallest x value, which happens to be a negative 3. And I want to collect all of the rectangles all the way up to a 1. And again, my formula says that I integrate the area of that cross-section. And this is the area of the cross-section that we are interested in. So we would integrate the negative 2x plus 3 minus x squared times 4. Again, these are all calculator problems. You put that in your calculator, allow it to calculate, and you get 42.667. Always go to the thousandths place, always. Unless it says otherwise. That is our default. On the AP test, if you're even 1/1000th off, you will lose the point. I can't stress that enough. I don't want you to do beautiful work, write your answer wrong, and lose credit. Okay? Thousandths. Go to the thousandths. So this would be the volume of this three-dimensional figure that would be created with rectangles as the cross-sections. Okay? Now let's use the same base. And let's say that we're going to use semicircles. Semicircles are going to be our cross-section that we're going to be working through. They're fine with that. More is better. If you use more than the thousandths, they're fine with that. It's their guideline is accuracy to the thousandth. All right, so semicircles. The formula for the area of a semicircle. So area formula for semicircle, half pi r squared, right? I mean, just half of the area of a circle. All right, so now let's think back to our figure. The half and the pi, that's a constant. Radius, we need to figure out how would we represent the radius here. This would be the entire part of the semicircle sitting right here at this base. The radius would be half of it, right? The radius would be half of that distance. So I actually already know this representation of that space. I'm going to half this. So let's do our integral. So I'm going to go ahead and take that half pi outside the integral just to be easy. So the radius, I think we agreed, we would take half of that space that we found previously. Half of that space. Now we also need to square that, right? Because that's the radius squared. So you can see the parentheses are going to be so important when you're putting them in your calculator. One slip and you're going to get a completely different answer. We need to be sure that this entire quantity right here, half of that location is squared, the whole thing squared. Okay, so we put that in our calculator. We're going, again, our bounds are the same. We're going from negative 3 to 1. We put that in our calculator and we get a volume of 13.404. Now, if you really don't like that there aren't units there, you could say units cubed if you wanted to. It's certainly not required. So let's think about that for a second. Does that make sense? Well, does it make sense that that's the same base? Does it make sense that using rectangles would give us more volume than using semicircles? That makes sense, right? Because the semicircle has less area. So that does make sense. Mm-hmm. Right. So you would have to think back to Riemann sums, when we worked Riemann sums and all the actual theoreticals behind integrals. The theory behind integrals is what it does is it adds up an infinite number of those. Like if you think about with the rectangles, it added up an infinite number of the rectangles. We use the rectangles to approximate, but the integral is actually perfect. It gives us all of it to infinity. And so it's going to collect every single semicircle in this area. That's what the integral will do. Okay? Yes? Mm-hmm. Sure. Sure, you sure could. If you really didn't want to deal with the constant, you could take that out as a fourth and put it outside with the other. You bet. All right, how are we on our first couple of cross sections? We okay? Here we just have a couple more examples. Yes? This height right here? No, because so if I drew a well, with this one it is because they're all height to 4. But with this one, the semicircles are not going to be. If you recall that the applet that we looked at, as the semicircle moved along the base, as the base grew wider, the semicircle grew higher, right? As the base grows narrower, the semicircle goes lower. It's just a function of the way that they're formed. Okay? But that one, we're told it's a 4. It has to be the same all the time. Otherwise, it moves. Okay? All right, let's take a look at, we have a couple of more examples to do. These will go, I think, faster since we are hopefully kind of getting the concept down. The next one says, our base is a circle. X squared plus y squared equals 9. So let's draw the base. So that's a circle with a radius of 3. Oh, kind of a circle. Just kind of go with me there. It's a circle. And our cross sections are perpendicular to the x-axis, and they are equilateral triangles. Now, equilateral triangles have a special area formula that go with them. It would be to your advantage. It would be easier for you to memorize this area formula for equilateral triangle. You do not have to. You can find it, area equals half base times height, but you're going to have to do some work to get the height. Okay, using this formula, we just take the side length. It's quite easy. But again, you don't have to. But that's what we're going to use when we so because our base is a circle and our cross section are going to be perpendicular to the x-axis, and they're going to be equilateral triangles. So I'm going to use the special equilateral triangle area formula. So we are perpendicular to the x-axis. So one of our cross sections is here. Let's visualize that's the base of one of the equilateral triangles. If you want to try to like draw in 3D, which I'm not a great artist, but that would be kind of a visual picture of one of the cross sections. So this would be an equilateral triangle, that would be standing up, kind of coming out of the board. So we need a representation for the side of an equilateral triangle. Well, first of all, our equation, x squared plus y squared equals 9, we really can't use it in that form. We are perpendicular to the x-axis, so we have to be in terms of x. We do not get to choose. Okay, that's the way it is. If we're perpendicular to the x-axis, we are with x. So let's solve this. So that'd be y squared equals 9 minus x squared. So y is plus or minus square root of 9 minus x squared. Okay, so now we have our equation in terms of x. So let's think about that for just a moment. If I want to talk about this distance right here, the distance from the x-axis to the top of the circle, that is measured by what? What measures this distance? So if I put in an x of 1, in what will I get this height? The positive one, right? If I put in an x of 1 in the positive square root of 9 minus x squared, I'm going to get this height. With me? So that gives me this distance right here. Now, my triangle spans the whole distance. I need the whole distance. And so I really don't want to mess with the negative square root of 9 minus x squared. So what could I do to gather all of the distance? Multiply by 2, right? That's what I need to do. So to gather so the side length of this equilateral triangle is going to be 2 times this. So that's what our side length is. All right, so let's start setting it up. So we're going to have an integral. Our side, we agreed, was 2 square root of 9 minus x squared. And according to this formula, we are supposed to square it. Then I'm supposed to multiply it by square root of 3 over 4. I'm just going to take that outside just for convenience sake. My bounds, my smallest x value is going to be a negative 3, and my largest is going to be a 3. I put that in my calculator, allow it to do all of the integrating for me. And my my volume turns out to be 62.354. And again, if it disturbs you, there are no units. You could say units cubed if you wanted to. All right, and that is our next, our one with the area. We have a circular base, and we're using equilateral triangles. The last example that we're going to do today is this one right here. We have a base of a solid bound by these particular curves. And it says for the solid, each cross-section is perpendicular to the y-axis. What does that mean for us? We have to be with respect to y, right? Again, with respect to y. So I'm going to have to change this and solve for x. This is going to be x equals plus or minus square root of y. So we need to fix that. All right, and the cross sections are squares. So our first step is to draw a picture of the base. So let's draw a picture of the base of our solid. So we have the parent parabola. And then we have y equals 0. Y equals 0 is the x-axis, so this part right here. And then we have x equals 2. That's this part right here. So our base is this section right here. That's the base of our solid. Okay? We are going to need to be perpendicular to the y-axis, so I'm going to draw, what do we are? Square. So I'm going to draw a side of the squares right here. That's one side of the square, a representation of the side of the square. So what we're going to have to do is come up with how do we show that in algebra. So area equals side squared is what we're going for. That's the area of our cross section. Now, when we were looking with respect to x, if you will recall, the function measured itself from the x-axis to itself. Okay, that's the distance that it measures. When we're with respect to y, the function measures itself from the y-axis. So if I use square root of y as my distance, I'm going to get this space in here. Is that the space we want? That is square root of y. No. We want that space, right? So I would take 2 and I would subtract out the square root of y to get this space. Are you with me? So if I use 2, it would give me all of the space in here, and I don't want it all. I want to take out this piece, which is represented by the square root of y. So to represent this location, that's going to be 2 minus the square root of y. That's what's going to give me that distance. Okay? And so using our formula, so the integral, we want to, it says side squared. We said side is represented by 2 minus square root of y. So 2 minus square root of y squared. That's my area formula for my cross section. And my bounds, recall, I'm with respect to y, so they need to be y bounds, not x bounds. So my lowest y value is a 0, and my greatest y value would be a 4. So we put that in our calculator, we integrate that, and we get 2.667. Okay, and those are some examples on volume by cross sections. Are we okay? Okay, let's try some of these on our own.